There's this idea when we're talking about solubility of like dissolves like. That is, polar compounds dissolve in polar solvents. Ethanol dissolves in water because the OH bonds are polar. In fact, both of these are capable of doing hydrogen bonding. So an ethanol water molecule will hydrogen bond with a water molecule. And both ethanol and water can be hydrogen bond donors and hydrogen bond acceptors. Nonpolar compounds dissolve in nonpolar solvents. So carbon tetrachloride is an example of a nonpolar molecule because none of the bonds are polar. Hexanes are also nonpolar. So carbon tetrachloride is soluble in hexane, not soluble in water. Ionic compounds tend to be soluble in water because the water molecule has a positive end and a negative end. The positive end is where the hydrogens are, and the negative end is where the oxygen is. So, ionic compounds tend to be soluble in water because of this. The hydrogens can interact with the anion, as you see here, and the oxygens can interact with the cation, as you see here. Of course, those interactions aren't always strong enough to make solubility, which is why there are some ionic compounds that are insoluble, as you saw in the solubility chart. Here's a graph showing how temperature affects the solubility of some substances. Notice, most of these purple lines are slopes upward, and these are mostly ionic compounds. For almost all of these ionic compounds, the solubility increases as the temperature goes up. One exception is the lithium sulfate, which at 0 degrees you can get 35 grams of lithium sulfate to dissolve in 100 grams of water. By the time you've gotten to 80 degrees, you can only get 30 grams. For all of the other ionic substances here, the solubility increases as the temperature goes up. For potassium nitrate, this is really steep. At 0 degrees, you get 15 grams of potassium nitrate in 100 grams of water. At 45 degrees, you're up to 80 grams. Now, the blue lines, their solubility goes down significantly as temperature goes up, much more significantly than the lithium sulfate. And these are HCl and SO2. Notice there's a pressure listed here. This is because these substances like to be gases. HCl is a gas unless it's dissolved in water, and the solubility of HCl in water decreases as the temperature heats up. That's because those HCl molecules are more likely to escape into the gas phase as they get hotter and hotter and have more kinetic energy. Same with sulfur dioxide. For gases, the pressure also affects the solubility. When you open a bottle of soda and pour it into a cup, you see it foams. This is carbon dioxide escaping from being dissolved in the water to becoming a gas. Why does it not escape when the lid is on? That's because the pressure is higher. So when the bottle is closed, there's high pressure and thus high solubility. When the bottle is opened, however, this lowers the pressure. Whenever you open a bottle or a can of soda, you hear the hiss. That's pressure escaping. This lower pressure reduces the solubility. And so you get the foam. Now for some quick terminology. A saturated solution contains the maximum amount of dissolved solute in a given amount of solvent. Saturated solutions are solutions that have as much solvent as their solubility. You can't get any more solute to dissolve at that temperature. Saturated solutions are in dynamic equilibrium. You know a solution is saturated when you've added enough solute that no amount of stirring causes all of the solute to dissolve. But what you'll have is an equilibrium between dissolution and recrystallization. In an unsaturated solution, the concentration of solution is less than the solubility. So since the solubility represents the maximum amount of solute that can dissolve, the concentration of a saturated solution is equal to the solubility. For an unsaturated solution, the concentration is less than the solubility, and that means you could keep adding solute and dissolving it. Now, if you have a substance that is more soluble at high temperature, and you heat it up and dissolve as much solute as you possibly can, and then you cool it down, you end up with what's called a supersaturated solution. Right, so supersaturated solutions contain more solute. The concentration is greater than the solubility. Supersaturated solutions are unstable, and if you disturb them, the solute will crystallize. Here's an example. One of these reusable heating packs. They start out as clear liquid, and then there's a metal disc inside, and if you flex that metal disc, all of a sudden you see the bag get hot and it turns white as a solid forms. That's because it's got a supersaturated solution inside. Now, that'll stay warm for quite a while, and what you do afterwards to reset it once it cools down is you put it in boiling water until it becomes completely clear again. So, the substance inside here is what we call an endothermic solution. In other words, adding heat increases the solubility. If you had an exothermic solution, you would get the opposite effect. So, here's an exercise. We've got 9 grams of KCl dissolved in 20 grams of water at 20 degrees Celsius. Is the solution saturated, unsaturated, or supersaturated? Pause and work it. I'll give you a hint. Figure out how many grams you'd have in 100 grams of water and compare it to the solubility. Once you've got your answer, you can unpause and check your work against mine. To find the answer, we need a number that we can compare with the solubility. We know that we have 9 grams of KCl in 20 grams of water. How many grams of KCl would that be in 100 grams of water? So, 900 grams of KCl equals 20x. And so x equals 900 over 20, which equals 45, I think. Let me double check my math. Right, so our solution then contains 45 grams of KCl in 100 grams of water. And we compare that with the solubility, which is 34 grams of KCl in 100 grams of water. And so our concentration is greater than our solubility. That means we are supersaturated.